Hey everyone, we hope you're having a great summer and a wonderful time at Touch Tomorrow. My name is Clarice.
My name is Ramesa. We can't wait for you to join us on this math modeling adventure into machine learning and what it does in the real world.
So nowadays, robots are very smart. Cameras, programs, you name it, they're all able to recognize what's around them. However, there's still an important difference between robots and people. While you and I can automatically recognize what's going on, robots need to be taught what their surroundings mean. For example, a robot might see a bird, but not exactly know that it is a bird.
By now, there's probably a big question on your mind. How do robots see in the first place? Well, that's what machine learning is for. Machine learning, which is a field of computer science, teaches computers how to make decisions and predictions. Here, data scientists and computer programmers feed machines data and use code to teach them new patterns and analyses.
So now that we know what machine learning is, what is image classification? Image classification is the type of machine learning that teaches robots what an image means in real life. Using machine learning, we can train robots to understand that this image here is actually a cat. But as we mentioned earlier, this isn't very easy to do. A computer cannot really tell the difference between a dog or a cat, or even a book for that matter. As you can see, this image of a cat is actually stored as a grid of numbers on a computer. These numbers represent different amounts of red, green, and blue light, the three primary colors of technology. What the computer sees isn't a cat, but rather it sees a bunch of numbers. So our challenge today is to use image classification to turn the grid of numbers into a single label like a dog or a cat. But why is image classification so important in the first place?
Image classification doesn't just exist in sci-fi movies. In fact, it already is a really big part of our lives. In the field of medicine, doctors can use programs to categorize different diseases. For example, doctors apply image classification to X-rays to identify whether someone could have lung cancer or not. This makes it a lot easier and quicker to form a life-saving diagnosis. Image classification also makes facial recognition possible, from using your face to unlock your iPhone to catching criminals and tracking hundreds of passengers at airport security. Facial recognition is integral to protecting privacy and maintaining security. Going back to machines, image classification is helping turn self-driving cars into a reality. Autonomous vehicles rely on machine learning algorithms to learn how to avoid obstacles, safely navigate busy roads, and protect their passengers from harm.
So now let's look at specific examples of image classification in the real world. Affectiva, a company based in Boston, Massachusetts, is already using image classification in real life. Affectiva develops convolutional neural networks, or CNNs. We'll learn more about this later, but for now, just think of it as a mathematical model to recognize faces and facial expressions and ensure the safety of the drivers or passengers in taxi services like Uber or Lyft. Affectiva uses image classification to recognize the driver's emotions. So for example, if a driver on the road looks tired or sleepy, Affectiva can alert the driver to stay awake so that they can stay safe. This same program can understand when a customer is satisfied or upset with their taxi service based on their expressions alone. And finally, the most important way this company uses image classification is to determine whether the traveler is actually safe inside the car. So if a passenger looks scared, then Affectiva could alert police to follow the car to ensure the safety of the passenger.
Here's a bit of a different example, just to prove that image classification goes beyond the realms of traditional science. Disney's animation studios use image classification to improve their digital characters. By running programs that detect different faces and emotions, Disney animators can check how realistic their characters are and make sure that everyone keeps their face in the middle of action. Here you can see an example of what that looks like. The green squares around each character indicate that a program has detected a face at that given location. This information can actually help animators to detect what shows up on screen.
Our last example might be the most unbelievable. Uber ATG, a branch of Uber dedicated to autonomous vehicles, is using image classification to make self-driving cars. Self-driving cars are cars that are able to drive on the road by themselves without help from a driver. With image classification, self-driving cars can see other moving cars and pedestrians around them so that they can navigate roads safely. Self-driving cars also use image classification to detect road signs and the color of the traffic signals so they know when to drive and when to stop. This can tell drivers how to drive safely, where to turn, and what part of the roads to avoid. As you can see in the left image, image classification is being used to color code the roads, cars, and other pedestrians. In the right image, you can see image classification being used to draw bounding boxes around cars, people, and other objects in the video. All of this is being done thanks to a stereo camera that is mounted at the top of the car that processes the video.
To make image classification possible, data scientists and computer scientists program neural networks. Neural networks are basically a collection of nodes made to mimic the human brain and the nervous system, taking in new information and making decisions based on that information. Just like how our brain spreads input from using neurons, neural networks nodes spread information and make decisions for its system. So in this way, neurons and nodes basically serve the same purpose, taking an input to choose an output. They even look the same in scientific drawings. For today, we'll be looking at convolutional neural networks, a group of neural networks specifically programmed to analyze images.
Our brain needs more neurons to analyze more complex information. So to mimic this in computers with machine learning, we add different layers. Each layer in a network connects to each other, stacking one on top of the other to add new interpretations to make stronger conclusions. The more layers a neural network has, the smarter its decisions become. In this diagram, we pass in an image of a boat for our input. This image will go through every layer to be analyzed and output the probabilities that this image is either a dog, cat, boat, or bird. The two main types of layers for convolutional neural networks are feature extraction and classification. So the first thing that a CNN does is extract features, analyze all the images it's given to find specific features to analyze. Neural networks do this by calling a series of algorithms, which are a standard set of rules, procedures, as well as instructions used to calculate common problems. You might have already used some algorithms yourself when you're doing long division or even solving a Rubik's Cube. Once the neural network has extracted enough features, it will try to classify each image into any of the categories or labels that it's given. This can be done by flattening its features, which is a process of converting data into a grid of input, using more algorithms to calculate the probability of an image belonging to each category, then returning the most likely group. So in this example, our output shows a 94% chance that the image is a bird or a boat. In contrast, there's only a 1% chance that this image is a dog or a cat. So this network will eventually return a boat, showing that this image does in fact contain a boat.
Now that we generally know what a neural network consists of, let's go into the specifics of how a neural network is built from. Whenever data scientists are building neural networks, they can define their characteristics, for example, the number of times it runs through the data or if there are any conditions it should look out for. These characteristics are called parameters, which strongly influence the patterns neural networks use to categorize images.
There's countless parameters that programmers might use to design their neural networks and maximize their accuracy and efficiency. Here, we've listed 4 that we think will be the most helpful for today's problem. The first is epochs, which defines the number of times a network runs through the entire dataset. Next is shuffling, which defines how often the dataset is reordered. This introduces an element of randomness that ensures our model can be more accurate in the real world, where it's not really possible to get used to one specific group of data. We can also control weights, which tell the model to favor choosing one category over the other, which is especially helpful when a dataset has a disproportionate amount of one image compared to another. The last parameter we have listed is early stopping. This is a signal that tells the model to stop learning or training when its accuracy starts to lower. You'll get to play around with these parameters later today and can learn more about them in our additional documentation.
Because machine learning is an established field in computer science, there's already a lot of resources out there. For today's challenge, we recommend you use Google Colab. Google Colab is an interactive development environment, which is any application where programmers can run and test code. Produced by Google, Google Colab makes it really easy to code in Python for data science and machine learning. Another resource that a lot of data scientists use is Keras, which is a library of existing neural networks that data scientists can import into their own programs and modify as needed. While we've already provided a model for you to tinker with, we encourage you to explore Keras to dive deeper into machine learning.
Perhaps the most important part of training a neural network is collecting data. Thanks to the improvements in computer processing, we can use thousands of data points, or images in this case, to train a neural network. We generally divide our data set into 2 parts. Training and testing. About 80% of all our data is used in training, a stage where the computer learns different patterns and adjusts its parameters accordingly. Within this training set, we save about 20% for validation. We'll use this data set when we're training the model to see how our model performs at different stages and adjust our parameters as needed. We'll save the remaining 20% for testing. This is a very special group of data that we only run once after training our model to see how our model performs with unfamiliar data, just like it would in the real world.
We're nearing the moment we've all been waiting for, the daily challenge. But before then, here's a quick review of what math modeling is. In short, math modeling is the use of math and research to make predictions about the real world. In this case, you'll use math modeling to create the best neural network that you can. There are 6 key steps to approaching a math modeling challenge, as shown on the screen. First, identify the problem that you're trying to solve. What's the exact question, and how would you define a successful answer? Afterward, you need to make assumptions and define the most important factors. Are there some parameters that you'll prioritize over others? What level of accuracy are you hoping to achieve, and why? How would you implement these parameters in code? Researching can be the lengthiest part of any math model, but is very important in finding relevant information and directing your next steps. Make sure that you cite your sources and connect your research to your written solution and model. Next, write down all the equations to solve the problem. Equations can take up many forms: written text, diagrams, or even pictures. Sometimes you can write standard equations, like the one that we use to calculate profit, and other times you can make your own. For this problem, consider graphing the relationship between different parameters and your accuracy. This can help guide your code and math to find the optimal solution. Then try to model your data. Keep training, keep changing parameters, and make sure that your model keeps adjusting to ensure that your model is accurate and relevant to your data. Last but not least, analyze your final product. What went well? What went wrong? How can you improve it? Can you use this model for other data sets? What does this model say about machine learning and image classification? Remember, there is no right answer. We're looking for creative, well-explained, and applicable solutions. Notice how some arrows go in multiple directions. That's because you don't always follow these steps in the given order. Don't be afraid to repeat steps if you need to.
Now comes the fun part. Your task is to make a convolutional neural network that can classify images of cats and dogs. This is a really common exercise that uses everything we've learned today and the fundamentals of machine learning. Keep track of what parameters you use and change. Report them back to us in your solution even. What's the highest accuracy you can achieve? What are the steps you use to reach that point? Are there any parts of the model that you'd like to change with additional time? You can find today's problem on Touch Tomorrow's website, and be sure to use our starter notebook on Google Colab. The top 3 submissions from each day will be graded for their creativity, the quality of their explanation, and their real-world applicability, and eventually be recognized and receive an award at our closing ceremony.
Now it's time for you to tackle this problem. Please submit your solutions, which should be no longer than 1 page double-spaced, by tomorrow before 10 a.m., and you can find the form to submit for each problem here on the Touch Tomorrow website, or on M3J's homepage, which is mmmjam.github.io. On either site, you can find helpful resources and the written problem under the machine learning section. If you have any questions or need any clarification on a part of this problem, please email us at mmmjam.team@gmail.com. Thank you so much for tuning in. We hope you learned something today and enjoy the problem. Good luck, and see you tomorrow.
The people you saw in this video are current juniors and seniors at the Massachusetts Academy of Math and Science, a STEM immersive high school located in Worcester, Massachusetts. In collaboration with WPI's Touch Tomorrow, our student-led team was able to organize the entirety of the Massachusetts Math Modeling Jam and bring it to you this year. Inspired by a math competition we all competed in junior year, the MMM Jam is just a small taste of the hands-on learning and incredible opportunities that this city has to offer. In fact, it's these kind of events that have inspired all of us to continue learning about science, technology, engineering, and mathematics in college and beyond. If you live in Massachusetts and want to check out more events like this one, be sure to look at WPI, Touch Tomorrow, and Mass Academy at the websites here. Thank you for watching, keep exploring, and happy modeling, everyone!